In this final week of our Astrotech MOOC, we're going to bring together all of the science and technology that we've learnt throughout this course in order to address one of the major challenges facing science today, and that's to try and understand the nature of the dark side of our universe. Now, less than 5% of our universe is made up of a material that we call baryons. That's the stuff that you and I and the Earth and the Moon and the Sun and all of the stars and galaxies that we can see, that's all made up of baryons, and it accounts for just under 5% of our universe. Now, the rest of the universe is dark. We can't see it, we can't touch it, but we know that it's there because of the effect on the things that we can see. Now, there are two entities on the dark side, dark matter and dark energy. And these two dark siblings are currently fighting out a cosmic battle of epic proportions, with the gravity of dark matter trying to pull everything in our universe together, and dark energy undoing all of its good work by causing the expansion of our universe to get faster and faster each and every day. Now, in this MOOC, you know we like to ask the question, how do they know all that? And today we're actually just going to focus on dark energy. That's the mysterious substance that's causing the expansion of the universe to accelerate. Now, cast your mind back to 2 weeks ago when we were using the physics of the Doppler effect to find very distant galaxies. We said that because the universe was expanding, those galaxies that were very far away from us were moving away from us, and so they were experiencing a Doppler effect. In fact, as the light from those galaxies come towards us across the universe, they experience lots and lots of little Doppler effects. So when we see those galaxies, their light is shifted towards the red. Now, in a universe where there is lots of dark energy, that expansion is accelerating. So the galaxies that are very, very far away from us, they're moving away from us at a much faster speed than they would be in a universe without any dark energy. So if we want to test our models of dark energy, all we need to do is measure the redshifts to lots of galaxies and compare that to the distances. And then we'll be able to see what dark energy is doing to the expansion of our universe. Sounds simple, but actually measuring distances to galaxies is quite tricky because we don't have a really, really long ruler with which to measure those distances. Luckily, we do have something called a standard candle. Now, this is an object that always emits at the same brightness, the same luminosity, wherever it is in the universe. Now, there are lots of standard candles that we can use in astronomy, but today we're going to focus on a special type of standard candle called a supernova type 1a. Now, this always emits at the same luminosity, but the further it is away from us, the dimmer it will appear to us. And so we can use its observed brightness to tell us how far it is away. Now, this image is just an artist's impression, but it shows on the left two nearby stars where the gravity of the small white dwarf star is pulling off the outer layers of its neighbouring red giant star. Now, remember, stars like our Sun and the red giant and the white dwarf that you can see here, they're supported by a source of pressure that's balancing the push of gravity. Now, as the white dwarf star collects more and more gas from the red giant, the force of gravity on that white dwarf star gets stronger and stronger until no source of pressure is going to stop that white dwarf star from completely collapsing under gravity. And that collapse results in a very violent explosion, and you can see the artistic impression of that on the right-hand side of this picture. Now, this very special type of supernova explosion is called a supernovae 1a, and the reason why it's so special is because the tipping point just before the white dwarf collapses and the explosion occurs, that always happens at the same mass. It's called the Chandrasekhar mass, and it's 1.4 times the mass of our own Sun. Now, because that explosion occurs always at the same mass, it's always going to release the same amount of energy, so it will have the same brightness. Now, for supernovae 1a explosions that happen much further away from us than ones that are nearby us, they'll appear to be much fainter, and so we can use the difference in the brightness to tell us how far away that explosion occurred. Okay, so we've got our physics, our standard candles, Now, what technology are we going to use to go out and find these rare supernovae explosions? Well, we're going to use exactly the same technology as the technology we used to find killer rocks last week. Now, there we were looking for objects that moved between different nights. Here we're looking for objects that go bang. Now, here you can see an image of a galaxy taken by the Canada-France-Hawaii telescope. And here is the same area of sky taken at a different time, but after a supernova 1A has exploded. And can you see the change in brightness? That's the supernova that you're seeing. Now, unfortunately, there are lots of objects in our universe that do go bang. So even if you find an object that changes brightness between different observations, how are you going to be sure that it's one of these special standard candle supernovae 1A that we're looking for in order to understand the mysterious dark energy in our universe? Well, in order to do that, we need observations of these supernovae at all wavelengths. And in order to make that measurement, we're going to need spectroscopy. And Andy's going to tell you about that technology in the next video.